So basically we have to prove that alpha composition beta intersection gamma is equal to alpha composition beta intersection gamma. So what we do, we take element here in this and we prove, and finally we show that that element goes in this also. So we start. So we take an element here. So take any x comma y belonging to alpha composition beta intersection gamma, then x comma y belongs to alpha composition beta and x comma y belongs to gamma. Correct? So see, when x comma y belongs to alpha composition gamma, what does it implies? It implies what? There exists z belonging to basically s such that x comma z belongs to alpha and x and z comma y belongs to beta. Correct? Now see, z comma y belongs to, basically we have, what we have to show? We have to show that we have to show z comma y is in beta. Correct? We have this, and x comma y in gamma. Correct? So z comma y belonging to beta implies y comma z belonging to beta, since beta is what? Beta is symmetric. So y comma z sorry. So what we have, y comma z is in beta and x comma y is in gamma. So x comma y belonging to, basically we need to show that something is in beta intersection gamma. Correct? Now what we have also, we have one thing more. We have alpha, we have alpha in gamma. Here I just write like this. Basically such that x comma z belongs to alpha, and alpha is contained in gamma, and what z comma y is in beta. This we have. Correct? So x comma z is in alpha. Now x comma z goes in gamma. Correct? So x comma z belonging to gamma implies z comma x belonging to gamma. Correct? Now z comma x and x comma y belonging to gamma. Here what is the logic, since gamma is what? Symmetric. Correct? Now z comma x, x comma y is in gamma. It implies what? It implies that z comma y belonging to gamma. Why? Since gamma is transitive. See, gamma is basically congruence. Being congruence, it is also transitive. It is also equivalence, and being equivalence, it is transitive. So z comma y is in gamma. So z comma y is where? it is beta intersection gamma, because zy is in beta, zy is in gamma, so z comma y is in beta intersection gamma, correct? Now x comma z is in, basically what we have, x comma z is in alpha and z comma y is in beta intersection gamma. What does it implies? It implies that x comma y is in alpha composition beta intersection gamma, and which implies alpha composition beta intersection gamma is subset of alpha composition beta intersection gamma. So this is required. So in this way we have proved that both these are equal to each other, and in this way K becomes what? Modular lattice. Hence K is a modular lattice. In this way it is proved. Here one corollary is that, corollary of this result is the lattice of congruences on a group is modular. This is corollary 1.8.4. So it's true, because when we talk about the congruences on group, we have already seen that two congruences commute with each other, correct? As you see, in proposition 1.8.1 last lecture, we have proved that if G is a group, then rho composition sigma is equal to sigma composition rho for any two congruences rho comma sigma on a group. So previous theorem deduce the deduction of previous theorem, that is the lattice of congruences on a group is what? Modular. So now we move to next definition. Let L be a lattice and A comma B belongs to L, then A is set to cover B in L. A is set to cover B in L if A is set to cover B, we just if A is strictly greater than B, and if there is no X, and if there is no x in L such that a greater than x greater than b, a lattice L is said to be and what is the notation of this? A is set to cover B. It is denoted by like this. A covers B like this. We write like this, correct? We say that A covers B if there exists no x in between this. There does not exist any x such like that, so that A is strictly greater than x and x is strictly greater than b, correct? Then we say that A covers B. Now next definition is that a lattice L is said to be semi-modular a lattice L is said to be semi-modular if for all A, B belongs to L, A covers A meet B and B covers A meet B, implies A join B and A join B covers means that if A covers A meet B and B covers A meet B, then it implies A join B covers A and A join B covers B for every AB belongs to L, correct? So if it is so, then we say that the lattice is said to be semi-modular lattice, correct? Now we prove proposition 1.8.5. Every modular lattice is semi-modular. Every modular lattice is semi-modular. We have to prove this, correct? Number proof starts from here. Let L be a modular lattice and let A B belongs to L such that A covers A meet B and B covers A meet B. Is it clear? So basically what we have modular lattice, correct? Now we suppose A covers A meet B and B covers A meet B. Now what we have to prove? We have to prove A join B covers A and A join B covers B, correct? So suppose there exists X belonging to L such that A less than or equal to X, A join B, strictly less than A join B. So suppose that there exists X such that A less than is equal to X, which is strictly less than A join B. So what is our claim basically? Our claim is what? Our claim is what? X is equal to A. This is our claim. If we prove X is equal to A, correct? If we prove X is equal to A, then we are done. Because we have to prove there does not exist X such that which lies between A and A join B, correct? So if we prove X is equal to A, then we are done. So now let's start. So what we have A less than is equal to X and strictly less than A join B, correct? Now if we take meet, then A meet B is less than is equal to X meet B is less than A join B meet B. See what it will be. What it will be. A join B meet B. Of course, A join B is what? Is greater than B, and we are taking here meet. So obviously B will come here, isn't it? As we know that A join B implies A join B is equal to B, and A meet B isn't it? By this fact, we have this thing. So obviously, since B is less than or equal to A join B, so obviously B will become here. So now the problem is that here basically X meet B so basically here equal cannot come. Why? Because here X meet B is not equal to B, correct? Why? For example, if you assume that if X meet B is equal to B, then what is the problem? Then what you have? X meet B is equal to B, it means what? It means that B is less than is equal to X, correct? Because B is equal to X meet B, so obviously it is less than is equal to X. And on what you have A less than is equal to X and B less than is equal to X. So A join B being least upper bound, it is X is the upper bound of B as well as A from here, correct? So A meet B is less than is equal to X. So A meet B is what? A join B is what? Least upper bound of A and B. So least upper bound is obviously less than or equal to the upper bound of A and B. X is the upper bound of A and B. So A join B is less than or equal to X, which is a contradiction. Why? Because X is strictly less than A join B. This we have already. So it is not possible, which is a contradiction. Which is a contradiction as x is strictly less than a join b. So what we have, so basically we have we have a meet b less than or equal to x meet b strictly less than b, correct? And since b covers a meet b, therefore a meet b is equal to x meet b, correct? Now basically remember our claim is what? X is equal to a. Now x is equal to a join b meet x. This will be or not? Because since a meet b is less than or equal to x, correct? So if we take meet, x will come or not? A join b is what we have. Sorry, we have this thing, x is strictly less than a meet b. So of course when we take meet of both a join b meet x, so x will come obviously, correct? So x will come. So in this way, now you see we can write like this: a join b meet x. How we can write? Since a is what? Less than or equal to x, we have previously what we have a less than or equal to x. Remember we have in the beginning we have a less than or equal to x and strictly less than a join b. This we have in the, isn't it? So we have a less than or equal to x, and L is what? Modular lattice, correct? L is modular lattice. So we can write like this: a join b meet x, and a join b meet x, x meet b, both are same. It will be what? A meet b, correct? Now this will be a. Why? Because you see a is always greater than a meet b. A meet b is what? It is the lower bound, greatest lower bound. So when you take join of that, a will come. So we have proved that